Yeah, now we're not. Okay, good afternoon, good morning, good evening, everybody. Welcome to this week's EMinar. We have Lindsay Higgy talking about capturing knowledge in code today. But before we get to her, I just want to give you a sort of a sneak preview of what's coming up in the next few weeks, and we're quite excited about the lineup. So next week we have Constanza Massanero talking about reduced order approach for probabilistic inversions of 3D magnetotelluric data. So enabling probabilistic inversions within full 3D. Then on the 24th of March, Juliane Huber talking about space weather and MT and how those two are related to each other. On the 31st of March, we have Colin Farquharson talking about EM-MT data inversion in general. The week after, just after Easter, NASA MacBell on ModEM, a user's guide. So for those of you who don't know how to use ModEM yet, that will be a very interesting one. And on the 14th of April, Vladimir Posyerev on EM inversion using neural networks. On the 21st, then, we'll have Kerry Key talking about Mare 2D EM, and I suspect how to use that and sort of the capabilities of the code. On the 28th, then, Randy Mackey on geologically consistent inversion of geophysical data, a role for joint inversion. And then we have a short break. And on the 19th of May, we'll have Malcolm Sambridge on optimal transport and geophysical inversion. And as some of you probably know, he gave the Gutenberg lecture at AGU recently, so that should be quite exciting. If you've registered, you probably know the procedure. All the previous talks and videos and presentations are available on the EMinar webpage. There you can also see if there are any changes to the program, and you can register for the upcoming events. And finally, again, I assume most of you are familiar with this. We are in a webinar, so things work a little bit different than a regular meeting. If you want to ask a question, please write it in the question and answers section. So there's a Q&A box that you can use to post your questions. We will monitor this, and if there's an urgent question, we can alert Lindsay and tell her to answer it. But usually we've been doing this at the end. You can use the chat, and in really urgent cases, you can also raise your hand if you really want to say something. Well, that's it from me in terms of the general introduction. So yeah, it's my pleasure to introduce or to welcome Lindsay Higgy. who has been doing her PhD at UBC with Doug Oldenburg on inversion of, well, a variety of geophysical data. Then went to Berkeley for a little while. I'm actually not sure if you're still officially in Berkeley, Lindsay, but now we just talked about this before the seminar. She is ready to move back to UBC and will take up a position as, I suppose, assistant professor at UBC and continuing her work on inversion. And with that, I'd like to hand over to you.
Thanks, Max. Right, I'll share my screen here. Perfect. Does that all look okay?
Yeah.
Okay, excellent. Well, thanks so much for inviting me, having me here. I'm thrilled to be a part of the lineup of EMinars. There's been some excellent talks, and so very pleased to have the opportunity to share with you some of the work that we've been doing in the Simpeg and GeoSci communities. And I also want to give a shout out and thanks to Sagi Kang and Doug Oldenburg, who are my co-authors on this presentation. So I want to start by acknowledging a number of folks in the Simpeg and GeoSci communities who have made some substantial contributions, which I'll be highlighting kind of throughout the presentation. And so first I want to say thanks to all of them. So Sagi Kang, who's currently at Stanford, Thibaut, who's at UBC GIF, Dom, who's now with Mira Geosciences, Joe, who's also at UBC, John, who's at DS, Devin at UBC, Rowan, who was at UBC and now CurveNote, and Doug, who's also UBC. So last week, for those of you who attended, Doug gave an EMinar on the fundamentals of inversion. And so this week, I'll be picking up on a lot of what he discussed and sort of the theory and the methods that he talked about, and sort of talking about how we translate that now into software and into an implementation. And so if you haven't seen his talk, I would encourage you to go take a look, because I will be sort of referring back to that throughout. And so if you did attend the talk, you saw this presentation, this slide last week. So I want to start with just kind of setting some context of what it is that we're looking at. And so I'm sure everyone here has seen a figure of this flavor before, where what we're doing in sort of any basic geophysical experiment is we've got some sort of source that's going to input energy into the subsurface. The subsurface is then characterized by some physical properties. And so in this case, if we're looking at EM or DC, we've got the Earth being characterized by electrical resistivity or conductivity, its inverse. And then the data that we measure depend both on the input energy as well as the physical properties of the subsurface. And then what we want to do in the inverse problem is then go from the data that we measured now to estimating a physical property model of the subsurface. And so last week, as a motivating example, Doug used the DC resistivity and induced polarization data from the Symmetry deposit and talked both about sort of linear inverse problems, so IP being a linear inverse problem, as well as nonlinear inverse problems, so DC resistivity. And we started actually, the first inversion you do is with the DC data, and we use that then to construct the IP problem. Talked about a few different approaches, so looking at L2 norms or LP norms, and so you can see these are the results that he showed, where we've got this mineralized zone that we're really able to characterize quite well when we use these more compact norms. And so there's a lot of good reasons for focusing on DC resistivity. It's a very illustrative problem. It's the foundation really for all of electromagnetics, and so it's a starting point for understanding the physics there. Also, in terms of learning how to implement a PDE, it's a very good equation to start with. It's one of the first you'll often see in a textbook that's talking about sort of finite volumes or numerical simulations. And then in terms of demonstrating the inverse problem, it's a nonlinear problem in conductivity or resistivity, and it's a really ideal example for showing the impacts of model norms and constraints and things like that. And so we've given quite a number of tutorials. So Doug's presentation last week. And then we also have a couple other resources I'll point you to. So there's the Pixels and Their Neighbors leading edge article that Rowan led a number of years ago. And so in this, we talk about sort of deriving the discrete finite volume representation of the DC resistivity equations. And then last April gave a tutorial at the Transform 2020 virtual conference. So this is by the Software Underground community. And we actually walked through the implementation of DC resistivity forward and inverse modeling with Simpeg. And so if you're curious to do sort of a deep dive into Simpeg, I'd encourage you to take a look at that. There'll also be an upcoming Transform conference. I believe it's in this April, and Soggy Kang will be giving a talk there as well. So I'd encourage you to take a look at that. But for this community, what I would like to focus on today is Maxwell's equations. So we're going to look at the full EM problem. And what we're going to do, and really sort of the goal of the talk today, is to sort of walk through how we start from the theory. So Maxwell's equations, sort of the fundamentals of inversions, and how do we capture that in code. And so the code base we'll be looking at is Simpeg. It's an open source software package. It's written in Python, freely available, welcome contributions, and I'll talk a little bit more about how to get involved later on. But these are the kind of the basic problems that we'll be looking at. So I'm going to start from the flowchart that was introduced last week, where we break down basically how we're going to solve the inverse problem in a number of steps. So in the top box here, we've got our inputs. So we've got some data that have been measured out in the field, and we hopefully have error estimates on those data. We need the ability to forward simulate, so some implementation where we can estimate or predict data given a model. And then we need some prior knowledge, if we've got geologic knowledge about the area that we're looking at, and the ability to build a reference model. From there, we'll go ahead and we'll define the inversion parameters. And so what it is, what I mean by that is what we're actually inverting for. We'll construct a statement of an inverse problem by choosing a Misfit criterion and a model norm. Perform the inversion, then you typically end up evaluating the results, and it's an iterative process where you're going to go in and adjust parameters and often end up running multiple inversions before you get to a final result that you interpret. So what we're going to do is we're going to walk through this kind of step by step. So we'll start in the first box here with the ability to forward model. So the basic equations we're working with are Maxwell's equations, and so they can be written in time or in frequency. And we've got fields and fluxes that we're working with. So E being the electric field, H being the magnetic field, B being the magnetic flux, J being current density. And then we've got our constitutive relations, which relate fields and fluxes through the physical properties. So Ohm's law, we've got the current density is related to the electric field by electrical conductivity. Similarly, B is the magnetic permeability times the magnetic field. So these are the basic equations that we're working with. As is common in many sort of EM geophysical experiments, we're going to assume the quasi-static approximation of Maxwell's equations, so we'll ignore displacement current. So let's focus in on the frequency domain equations. And what we're going to do is we're going to rewrite those equations in terms of one field and one flux. So in terms of the electric field and the magnetic flux density. And so these are the basic equations that we're going to start from, and we want to work through and discretize those. In order to do that, we also need to know boundary conditions on our domain. So we'll assume that the tangential component of the magnetic field on the boundary is 0. And then what we're going to do is we'll use a staggered grid discretization. So this is very common in EM experiments. And so what we'll do is we put the physical properties at the cell centers. So the conductivity and magnetic permeability are at the cell center. And you can think of those as basically filling the whole cell volume. On the edges, we discretize fields. So the electric field in this case, we got EX, Z, and EY on the edges, and then fluxes go through faces. So we can then go ahead, once we have this discretized, we approximate the equations in their weak form, and we can derive the finite volume discretization, and that's what it looks like. So I've glossed over the details here. If you're curious to dig into that, I encourage you to check out Eldad's book, as well as the Pixels and Their Neighbors article I referenced earlier. So now we've got 2 equations and 2 unknowns, and this is going to be what we're going to go ahead and need to solve. We can eliminate B and obtain a second order system in the electric field E. So now we've got a system that's basically of the form A times U equals some right-hand side. And so this is a very common system of equations that you end up seeing. And what we want to do is solve that for the electric field E. So there's a few properties of the matrix A that I want to point out. It's a complex matrix. You can see here we've got complex values because we're working in the frequency domain. It's symmetric. You can see here it depends on the frequency. So depending on how many frequencies you're working with in a given experiment, you need to solve a difference, or you need to solve this for every frequency. It's separable over frequency, so that means it can be parallelized over frequency. If we're doing an inversion, it depends on the conductivity. And so what we need to do is every time we update the model, this needs to be refactored so that we can solve it again. And so that's kind of the basic system that we're going to go ahead and work with. So now that we know the discrete system that we're going to work with, we can actually go ahead and implement that in code. And so this is what it kind of looks like when you're working with Simpeg. And we've tried to basically set up Simpeg so that it is, when you're writing out these discrete equations, it does very much look like the discrete version that you would write down in your notebook. And so we define omega, we get our operators like the edge curl, the physical property matrices for mu and sigma, and then we can assemble our A matrix. So we've got our curl transpose, mu matrix, curl, plus I omega sigma. So that's what our A matrix is here. We construct an object that acts like A inverse. And so in this case, we're not computing the inverse here. Anyone who's done numerical computing would know you don't want to compute the full inverse. But rather what this is an object that acts like A inverse. So whenever we multiply it by something, it will go ahead and factor and solve. We construct our right-hand side, and then we can go ahead and solve that system of equations. And so you'll notice here, I'm referencing this mesh object, and I want to show you a bit of what that is. So the way that we've implemented that is in a package called discretize, and that's within sort of the Simpeg ecosystem, and it's responsible for all of the meshing that we work with within Simpeg. So I'll show you a simple example. So here we're setting up a tensor mesh. So we define vectors of the cell widths in the X and the Y directions, and we input those and construct a tensor mesh. And so you can see we've got a cell here with a width of 3, 2, 1, 1, 1. That's the same as this vector here. Once we've constructed that mesh, it then has, because we've defined the geometry, it's got some properties. So for example, we know where all the cell centers are, or where all the edges are. We know its dimensionality, these sorts of things. So these are all sort of geometric properties that we can get right away. Because we also know the geometry, it means we can construct operators. So things like the edge curl, a gradient, a phase divergence, because those all just depend on the geometry. And so once we've constructed the geometry, we have access to all of those, as well as methods such as being able to interpolate or construct those inner product matrices we need for the physical properties. So I showed you a simple tensor mesh, but we also have other meshes implemented. So later I'll demonstrate to you a cylindrical mesh, which just assumes that we've sort of rotated a tensor mesh around an axis of symmetry. We also have tree meshes. So a quad tree in 2 dimensions or an octree in 3 dimensions. And I highlight Joe here. He deserves a lot of credit for the current octree implementation and how efficient it is within Simpeg. And there's also a curvilinear meshes. And so if you wanted to try adjusting a mesh to a surface or something like that, that's implemented as well. And these are 2D plots, but we also have the 3D implementations as well. Okay, so I showed you how we sort of solve the system, but glossed a little bit over how we construct the right-hand side, as well as how do we get the data that we're looking for from the simulation. So I want to touch on that now. So there's two components. If we first start with the sources are going to be how we define what that source current density is. And that could be an inductive source. So if we're talking about, for example, an airborne EM experiment where we've got a loop, it's an inductive source, or these could be grounded sources where we've got electrodes connected to the surface. And both of these types are implemented within Simpeg, and we just need to basically define where those current densities are on the mesh. So that gives us our right-hand side. We go ahead and solve. And then once we solve, we actually have what we obtain is the electric field everywhere on the mesh. But typically we're measuring fields, either the electric field or perhaps the magnetic field, only at specific points. So we then need to interpolate to receivers. If we're using something like the magnetic field, we also need a step in there where we're going to take the curl to get the magnetic field from the electric field. So we can kind of think of that basically as the predicted data being some operation on the fields that we obtain that might depend on the frequency. So all of this within Simpeg is captured and sort of contained in a survey object. And so what we do is we define our receivers. So here, for example, our sources. So here, for example, if we're looking at a magnetic dipole source, what we do is we define that for each frequency that we're operating in the survey. That source keeps track of which receivers are listening to it. So if we've got an airborne experiment, perhaps we have a receiver that's coincident to that. Or if we're doing a ground survey, maybe we've got a whole bunch of receivers on the ground that might be listening to that source. The source is defined for each frequency, and it has a location. Then the survey is basically the object that keeps track of all of our sources and all of this geometry. So now we have sort of all of the pieces that we need to solve Maxwell's equations, construct that right-hand side, and obtain the data that we want from those equations. So the way that we bring all of that together is in a Simpeg simulation object. So if we want, for example, to work with frequency domain, that's what we've been showing throughout. We import that from the Simpeg electromagnetics library. And then we construct this simulation object. So here we worked with the electric fields as being the thing that we're solving for. So we've got an electric field simulation. It takes a mesh, which has, again, all of the ability to create all the operators that we need for Maxwell's equations. The survey, which gives us everything we need to construct the right-hand side and obtain data. A solver, so we choose basically how we want to solve and factor that A matrix. And then this sigma map, and I'll come back to what we mean by these mappings later on. And so we've got this simulation, and when we actually call the fields method on that, given a model, it can go ahead and compute the electric field for all of the frequencies that we're working with. And then from there, we can compute predicted data, which then take basically the fields everywhere on the mesh and give us the fields that we are interested in looking at. Another piece is that we need from the simulation is also the ability to calculate sensitivities and the adjoint if we're using second order methods. And so I won't go into too much detail here other than to highlight that this is a necessary piece and this is all implemented. And so we need basically the derivatives of the data with respect to our model parameters. And so we start with what our data are. So that P matrix, again, is basically the transformation of the electric field to the data that we're measuring. So we take that derivative. And then we need the derivative of the fields on the mesh with respect to the model. And that actually requires a solve. So here we actually have to go in and we're going to need to solve. We'll need to invert this matrix again. So it's a computationally expensive piece. J is typically a very large, dense matrix if we've got a large survey. So for example, if we have a mesh with 1 million cells and we're collecting 100,000 data, that J is 1 million by 100,000. So that's 100 billion entries. So that can be a very large matrix. So if your memory limited, depending on where you're running an inversion, we would typically, instead of forming that matrix, compute its product with a vector. And so all of that is implemented within Simpeg. All right, so now what I would like to do is actually show you a bit of this in action. I know that we worked through the frequency domain equations. In this case, I'm going to switch to the time domain. Observing the physics and sort of understanding the physics is a little more intuitive in the time domain. And the way that we have the time domain actually implemented in Simpeg is we are doing discrete time stepping. So we've got the frequency domain implementation where we solve the frequency domain equations, and the time domain implementation does actually do the discrete time stepping. And so I'll show you kind of what that looks like. So here, this notebook is available to you if you want to take a look on CurveNote. And when I share the slides, all the links will be in there if you would like to follow along. And there, from there's a link to go ahead and actually run that. So this is what the notebook looks like. So we can go ahead and import some of the packages that we need. So these are all kind of standard Python packages, and these are packages that are specific to Simpeg. The model that we're going to work with is a sphere in a half space. So we can define, we've got a resistive background and a conductive sphere. And then we also have our air cells defined. And you can define the geometry of the sphere, its depth and its radius. For the survey, what we're going to do is we're going to consider something like an airborne survey where we've got the source immediately above that sphere, and we'll use a coincident source and receiver. So the receiver is coincident with that source. And we'll collect data at a number of times. Here we just define the source location and the receiver location. And then an important thing to consider when you're designing a mesh for any EM experiment is that we make sure that we satisfy that the mesh is large enough to satisfy those boundary conditions. So remember that we need the tangential component of the magnetic flux to be 0 on the boundary. So we basically just need the fields to have sufficiently decayed by the time they reach the boundary. And the diffusion distance is one way to get a sense of how quickly the fields decay in the time domain. So that's why I've printed that out here. We go ahead and we define a mesh and just kind of want to make sure that my boundaries go well beyond this, which they do. So the axis of symmetry is here at 0. And so this is a cylindrical mesh. So you can think of it being sort of rotated around. We've got sort of fine cells near where our survey is going to happen. And then we've got padding cells to make sure that those boundary conditions are satisfied. Next, we just put our model on the mesh and we can take a look at what that looks like. So we've got our resistive background, a conductive sphere, and our air cells, and our source and receiver up here. As I mentioned before, we create the Simpeg survey. So we're going to look at this point, we're going to look at dB/dt data at the times that we specified earlier, and we'll look at the Z component. And then for the source, we'll use a circular loop with a radius of 1 and a waveform that's a step off. If you had other waveforms that you wanted to look at, there's tutorials on how to connect with those and plug those in. To set up the simulation, we need to also specify which times we're going to do the time stepping at. And so this is typically a finer sort of time discretization than when your receivers are listening, because we do want to make sure that we're sort of accurate in our time stepping. And so that's what this is. We set up that simulation, and then we can go ahead and solve. Then this is just a bunch of plotting code. So if you're curious to see some matplotlib, you can take a look at that. But what I really want to show you here is now we can go ahead and visualize the results. And so one of the things we've tried hard to do within Simpeg is to basically expose to users and researchers the ability to go in and visualize fields and fluxes. You know, often when you run a simulation, all that you get out is the data at the end. But being able to go in and look at the currents in the magnetic fields can be quite insightful. So here I want to show you what that looks like. So let's just start by looking at the background model. And remember, we're doing an inductive source experiment. So this orange dot here is where our source is, and we've got a loop. So let's take a look at the current density. So basically immediately after shutoff, which is what we're going to be looking at here, we have circular currents that are induced into the earth. So we had a circular current in that source. As soon as we shut that off, we have currents induced into the subsurface. So yellow is going into the page and blue is coming out of the page. So we've got this circular motion, and we can go through time and we can watch those currents diffuse into the earth. And so folks who are familiar with time domain, they'll know there's a specific angle at which these currents diffuse out at. Goes back to Misfit-Nabigian's paper. And if you actually plot this out, you should see that we're at this 30 degree angle here where these currents are diffusing down and out through time. Okay, if we switch back and let's take a look now at what happens when we have our sphere present. And we'll look at our currents. So we've put our sphere back in and we'll look at the currents here. So again, immediately after shutoff, the currents are still sort of in this resistive background. And then as we go through time, we can see that they're starting to interact with the sphere. And then shortly, those currents become much stronger in the sphere. So it's kind of hard to see, but you can actually start to see that the currents are located basically entirely on the outside of the sphere. This sort of like skin effect where we've got the currents really focused on the outside of the sphere. And as I keep going further and further, you can see basically all of the current is really concentrated in this sphere. And as we go later in time, you'll see them start to diffuse in. But it takes quite a while. Diffuse down and in. And then, so what we're actually measuring at the surface is dB/dt. So you can take a look and see now what our data are. And so we can take a look and see at any given time the dB/dt field. So we see we're looking at the vertical component here. And we can flip back and forth and see how that changes between the sphere present and just that background model. And then finally, we can plot up what our predicted data are. And so we can see the background is this dashed line, and we can see the impact of the sphere in sort of these intermediate times, where early on I showed you, those currents were just in the background. This is where they're interacting with the sphere. And then if we go later and later in time, you'll see that they diffuse away. So that's a time domain simulation using the cylindrical mesh with Simpeg. And this is all available to you. And I'll again share the links at the end and some instructions for getting up and running with this. So this is the link here as to where you can find that. Okay, so at this point, we now have the ability to forward model. And I'm assuming that we've got some field observations and our prior knowledge at hand. And so now we're going to move on and we're going to start to work through the inversion. So the first step here is now to define the inversion model parameters. And so the question we're asking here really is, what parameters are we inverting for? Are we going to invert for conductivity? Do we want to invert perhaps for log conductivity? This has the benefit that enforces positivity, right? If we just worked only with conductivity, we need to somehow impose that it stays positive. This also can be a bit more of a perhaps natural scaling to sort of search for parameters in, because conductivity does tend to vary somewhat logarithmically. We do see orders of magnitude changes in conductivity. And then in an EM experiment, we typically we know where the air-earth interface is, and we don't really want to be inverting for air cells. So we maybe want to set those to be inactive. And so what we want to do is perhaps invert for log conductivity below the subsurface. So if these are the model parameters that we're working for or working with, and these are what we want to invert for, we then need some mechanism to get from log conductivity, our model parameters, log conductivity below the subsurface to physical properties everywhere on the mesh so that we can run those simulations. And so the way that we do this is through a mapping. And so what mappings are is it's basically a function that, given a model, gives us back the conductivity or a meaningful physical property in any sort of simulation on our simulation mesh. And so in this case, there's two steps that we would perhaps take. So mappings, they can be composed. So the first thing we want to do when starting from our model parameters here, we want to add back those the inactive cells, sorry. So add back our air cells. And then this is in log conductivity space. And so then we need to take the exponential so that we're working with a physical property. So this is a simple example of a mapping that can be composed. This could also include parametric models, for example. So if instead of treating this, as a physical property, or sorry, as log conductivity at every voxel, we could equally parameterize this as perhaps, the log conductivity of a top layer, of a bottom layer, and maybe a slope and an intercept to define the interface between those. So we would have then 4 parameters that then need to be mapped through. And so all of those implementations are possible all through mappings. And another important point with this is that at each step, we need to keep track of all of the derivatives so that we can go and compute the sensitivities in the inversion. And so if you're constructing a parametric model, we would need to have all of the derivatives for that as well. So now we know what we want to invert for. The next thing we want to do is choose a misfit criterion. And so Doug talked about a lot of the background on this last week. And so if you want to start sort of from the continuous version and get to the discrete version, I would encourage you to take a look at his talk. And so we're starting from some data misfit term. And so we've got our observed data, that's DOBS. Our functional f of m, this is our forward operator. So we've got our forward simulation that we know how to compute predicted data given a model. And then the uncertainties in our data, these are captured in this WD matrix. So WD is a diagonal matrix where the entries along the diagonal are 1 over the standard deviation of each observed data. And we would typically, a common way to represent these is to assume that there is some percentage error plus a floor for each datum. So now we want to translate this to code. And so what does that look like in Simpeg? So there's 2 pieces that we use to basically construct what we need here. The first is the data class. So what the data class is it's going to keep track of our observed data, so this DOBS vector. The survey geometry, so that we know what each datum means, so what each datum, which source and receiver it's associated with, as well as uncertainties. And so if you set a relative error and a floor, these can be either scalar values, or if you needed, for example, if you wanted to assign a different relative error for each frequency in your survey, these also can be vectors. And so this data object basically keeps track of everything that we need to get DOBS and to construct this WD matrix. Then what we need to be able to compute the data misfit is we need to plug in, we create this object that basically also then keeps track of the simulation. So if we want to work with an L2 data misfit, it's instantiated or created with the data here. So again, it will know how to construct DOBS in this WD matrix, as well as a simulation, so that we can have access to this forward operator. Once we've constructed that, Now, then we have everything that we need to go ahead and compute phi d given a model. We also can compute its derivative. And if we're using second order methods, we need the Hessian as well. And so that's what this deriv 2 is. So those are all the components that we need basically to evaluate phi d and its derivatives given a model. Okay, so the next piece that we're going to look at is how do we design a model norm? So we start from a basic Tikhonov regularization where we've got a smallness and a smoothness term. Here I'm just showing sort of a one-dimensional problem. If you had 2 dimensions or 3 dimensions, we would then just be adding sort of the alpha x and the equivalent derivatives in the y and z dimensions as well. So we start from our continuous version and we discretize that. Or we've got a number of choices and things that we can set. So we know what our model parameters are. We know what M is. We can choose what our reference model is. We can choose these alpha weights. So they give us a balance of how smooth or close to a reference model do we want our model to be. We can choose whether or not the reference model is in the smoothness terms. And so this is something that you can explore if you do have a complex reference model with different surfaces and things like that in there. This will make a difference. And then although I've written a 2 norm here, as Doug showed last week, you can change and explore how using different norms in this regularization or model norm change the inversion result. So this is all handled in Simpeg by the regularization class. And so it's from Simpeg, you import regularization. And here, for example, if we wanted to start with a Tikhonov regularization, it needs a mesh. So it's instantiated with a mesh. And we need that so that we can compute these spatial derivatives. Then the other parameters here have default values. So we've got default values for alpha s and alpha x, but these can all be replaced by user specified values. So that constructs the regularization. We also have, for example, the sparse regularization implemented. And so here you could go in and specify different norms that you want to be working with. And then very similar to what we did for the data misfit, now for the model norm, we've got everything that we need to compute its value and its derivatives given a model. So again, the first and second derivatives given a model. Okay, so we've got sort of the building blocks now of our inversion. And now we want to look at this box called perform inversion. So there's a lot going on in this one box. So I'm going to unpack it in a few slides here. So first, let's state what the objective function is that we're going to work with in the inversion. And so here we're treating this as a deterministic problem where we're going to use a gradient-based approach for solving the inverse problem. So we define our objective function as being composed of our data misfit and our model norm terms, weighted with some beta parameter, a trade-off parameter between them. And then there's perhaps we want to reach our target misfit, and we might have bounds on there. And so at this stage, there's a few pieces that we've highlighted that are sort of underlined here in green, and those are things that we have at this stage we've specified. So we know which parameters we're inverting for. We know how to construct our data misfit and our model norm. But these other pieces we haven't yet defined. So we haven't actually chosen how we're going to perform this minimization. And that's going to be influenced by if we have upper and lower bounds or not. We haven't specified how we're going to choose beta yet, and how we might update that during the inversion. And then similarly, how we define our target misfit. So we're going to work through those step by step in the next slides. And I'm going to start by looking at the optimization methods and the upper and lower bounds. So in Simpeg, in many geophysical inversions, second order methods are an approach of choice. And so an inexact Gauss-Newton method is quite common if we don't have bounds. And so that's implemented as an optimization approach. And so there, you can go in and specify things like the maximum number of iterations that the inversion can take, as well as maximum CG iterations under the hood. But those again have default values. If we do have upper and lower bounds, in this case, then we need an optimization method that can work with those. And so you could use something like a projected Gauss-Newton and define those bounds. And so these bounds, lower and upper bounds, these can be either scalar values. So if we know, for example, we want to enforce positivity, then we want to perhaps set a lower bound of 0 in a given problem. If those bounds are not set, so for example, here I didn't set an upper bound in this example, that assumes then it's infinity, so it's not going to impose any bounds. And so this then gives us sort of the machinery that we need to go ahead and perform that optimization. So then the next piece is, how do we define sort of beta, any sort of beta schedule that we want to work with, and our phi d star when we want to stop the inversion. What we use in Simpeg for this, these pieces, these are directives. And so what directives are is they are basically what we use to make any sort of parameter updates during the inversion, or anything that we need to basically orchestrate the inversion. So if we're going to use a beta cooling schedule, that's something that's changing during the inversion. And so directives are what handle that. And so let me show you kind of what this looks like. So let's start by asking, let's compute our initial beta. So if you wanted to, as a user, you can specify a beta value, but often it's sort of, it's not easy to sort of just, look at your phi d and your phi m and say, oh, I think I know what the trade-off parameter should be between these. So one mechanism to try and estimate that is to basically get a sense of the size of the data misfit and the model norms. And the way that we do that is by approximating the eigenvalues of the Hessian of each. So of the phi d, that would be J transpose J times the weighting matrix repeated. And then here, that's going to be controlled by the Wm transpose Wm. And so that basically tries to give you a sense of how large, what order of magnitude are, do we expect sort of the values for each of these to be. So we can estimate that using common sort of eigenvalue approximation techniques. And then we take the ratio of those and we can weight by a parameter that controls the relative importance. And so if I say I would like, early on in my inversion, I would like my model regularization to be approximately 100 times more important than my data misfit term, that's what this would look like. So within Simpeg, we define this directive that's going to basically, it needs to go ahead and compute these eigenvalues and sort of perform computations from each of these pieces to estimate that. Then the next piece is a common approach in EM inversions is to define a beta cooling schedule. And so basically to start with something that's going to weight the importance of the regularization very strong, and then as we progressively fit the data, sort of turn down the volume on that and try and fit the data more strongly. And so there's a few different things you can change in how you and how we sort of do this beta cooling. And so we can change the cooling rate. So for example, if we want to reduce beta every 2 iterations, that's what this would do. If you wanted to do every 4, you could change that to a 4, or every iteration would be 1. And then we define how much beta is reduced by. And so this example, I chose 4, but again, that's something that you can choose. And then finally, the last piece is defining our target misfit. And so, and Doug touched on this last week, but if we've got a model that's adequately fitting the data, the expected value of the data misfit is approximately equal to n, where n is the number of data. So that's if we've defined, defined appropriate uncertainties and have an adequate model. And so the way then that we define our target misfit is phi d star is some chi factor times n, where n is the number of data. And so basically what this does in the inversion is at the end of every iteration, it's going to ask, have I reached my target misfit yet? Yes or no. And if you have, then it will stop the inversion. So those are a few directives, but there's a lot of flexibility within sort of what directives are and what sorts of things you might want to be doing as an inversion is running. So a few other examples of directives that are quite handy is if you wanted to save, for example, an inversion model at each iteration. So at the end of every iteration, you ask the inversion, please save where I'm at. That's implemented as a directive. Similarly with the inversion progress, if you want to keep track of the beta and data misfits, you have access to those later. There's also more advanced things that you can do. For example, Doug showed the importance of using sensitivity weighting in potential fields inversions. And so if you want to include that and perhaps update that during the course of an inversion, that would be another example of a directive. The way that LP norms are implemented within Simpeg is that you first actually run L2 until we sort of we can't make much more progress, and then we switch the norms. And so this switching of parameters is also handled by a directive. So this is quite a number of examples, but basically the takeaway here is that a directive is basically anything that you want to be sort of changing during the inversion or sort of checking on values. So it basically kind of is used to sort of orchestrate the inversion as it's running. So that's the pieces that we need to run an inversion. So there's two pieces that come together within Simpeg to get sort of to bring all of this together. So we have the inverse problem. What this is it's basically this top line here of our statement of the objective function, as well as how we're going to perform that optimization. So this inverse problem takes our phi d, our phi m, and our optimization routine. Then our inversion takes the statement of the of our objective function or of our minimization problem here, as well as all of these directives. So anything that you want to be sort of orchestrating as the inversion is running. And so that's all, these are the directives that we talked about for this problem. So estimating the initial beta, using a beta cooling schedule, and then stopping the inversion once we've reached a target misfit. And from there, you can go ahead and actually run the inversion. And so here, Doug showed last week sort of a number of plots of inversion progress. And so reaching here our target misfit on the phi d curve, and we can see the model norm increases. And you can again plot that as a Tikhonov curve where we're looking at the phi d and phi m. So I'd like to show you an example. And we're going to look at, right now, we're just going to look at a 1D example, but we'll look at 3 different systems. So we've got a layered Earth model where we've got a resistive layer in sort of a moderately conductive half space. And then we've got a conductive unit that is much deeper. We look at 3 different systems. So we'll look at the resolve system, which is an airborne frequency domain system. We'll look at geotem, which is airborne, and that's a time domain system. And we'll look at nanotem, and that's ground-based, and that's also time domain. So we've got all looking at Maxwell's equations, but 2 different flavors and 3 different systems. So we've got our plot of the resolve data here, the real and the imaginary at 5 different frequencies. We've got our geotem data, which you can see is at later times than our nanotem data. This is looking earlier in time. This example was originally presented at the Airborne EM 2018 workshop, and we've got a paper from that that you can take a look at. And I've got the references all at the end. So what we're going to use for the forward simulation and calculation of the sensitivities is Simpeg EM1D. And so earlier I showed you the finite volume discretization, which we can use on cylindrical meshes or any of the 3D meshes that we have in Simpeg. But if you're working with a 1D problem, a very computationally efficient way of doing that is relying on digital filters. And so that's what Simpeg EM1D is. It's parallelized over soundings. And so if we want to run a large, large area, large airborne survey, that can all be done in parallel. And then we've got implementations for common frequency and time domain EM systems. So I want to highlight Sagi in this, is he's really led the charge on the development of the Simpeg EM1D code. And he ran this example here. So we start, and we can go ahead and invert each of these data sets independently. And so we get 3 different inversion results. We're using L2 regularization for each. I've got a plot on the left of the data and the fit to the data. And so the dots are the observed data, and the lines that we see are the predicted data. So in each case, we've adequately fit the data. And it's kind of interesting as you can really see the different sensitivities of each of these systems. Is that the, oh, sorry, this is backwards. The black line is the true model, and then the colored are the recovered from the inversion. So both the resolve and the nanotem are quite sensitive to the near surface. And so we can see that it looks like, we're picking up on this resistive near surface layer. Whereas the geotem is looking deeper, where we can hardly sort of see the influence of this resistive layer, but here we can see the conductive unit, and that's really not showing up in either of these. And so we can see, no one of these inversion results is really sort of adequately characterizing the model that we're trying to get to. But if we look at perhaps trying to combine all of these, we should have all the information that we need. And so that's maybe something that we want to do. Maybe we want to go ahead and run a joint inversion. So this is something that you can do in Simpeg. So in this case, we can define the composite phi-d, the phi-d that we want to work with in the inversion, is just being composed of these three misfit terms. And so we've got the phi-d that was constructed for the resolve. So this is looking at a frequency domain EM implementation. We've got one for the geotem. And so this is now looking at a time domain implementation. And we've got the nanotem, and this is time domain, but now at earlier times than the geotem. So these are actually 3 sort of different surveys and specifications of the forward simulation, but they're all sensitive to the same physical property, electrical conductivity. So let's go ahead and run our joint inversion. And so here we can see we actually get now a model that has features that are sort of consistent with each of these inversion results that we're seeing. So we're seeing that we are getting this resistive near surface unit, and now we are able to resolve this conductive deeper unit because we have sort of sensitivity from all 3 surveys combined, which no one on their own was really able to piece together. So this is all with an L2 regularization, but maybe we also want to try, as Doug showed last week, to get sharper or more compact units. And so we can also run a very similar inversion approach using an L0 regularization. And you can see that that really sharpens up and gives us much more defined units. And so this is a final comparison of the 2. So we've got our L2 inversion of result and our L0. And so I wanted to just kind of unpack a little bit what we have in terms of joint inversion capabilities within Simpeg. And so this was an example that we're looking at similar physics, but it was actually 2 different implementations. So one in time and one in frequency. And so those can all be combined. So each of these is basically treated independently in the inversion. If you want to work with different physical properties, if you wanted to do a joint inversion of gravity and magnetics, you would need to define some sort of regularization and coupling term between those 2. But again, that inversion, the construction of the data misfit would be very similar. Each simulation can be run on a different mesh if you needed to. So if, for example, with geotem, because we know it sees deeper, we perhaps want to use a larger mesh that goes deeper into the earth. But maybe that's not necessary for others. As long as you've defined mappings and ways to link those, each of this forward simulation meshes can be different. And as we talked about with the mappings, the forward simulation and inversion meshes, or the way that we define are the parameters that we're inverting for, those can, again, all be different. So the next example that I'll show you quite briefly is, again, a 1D Yam Inversion example. And this has been published in a number of places, so it's a bit of a nice comparison example. at Bukpranong. And so this is in Australia. And the floodplain region, they're trying to basically get a sense of why get a handle on sort of the salinization of the Murray River. So there's an irrigation district, and this is upslope from the stream. So there's fertilizers and things like that being applied up here. And then, yeah, trying to understand why this region is becoming more saline. So there were two different surveys run. In 2006, SkyTem, which is time domain system, was flown. And in 2008, Resolve survey was flown. This is frequency domain. So we'll look at the Resolve data. So we've got 5 different frequencies with Resolve, and you can see we've got, you know, the real and imaginary components, and we'll invert these data. We'll use Simpeg EM1D again, but in this case, what we're going to do is we're going to use a spatially constrained 1D inversion. And so what that is going to do is impose regularization that actually asks for smoothness between adjacent soundings. So we go ahead and invert those data, and we get back a conductivity model. It looks something like this, where conductive regions are red and more resistive regions are blue. And so, as I mentioned before, this is kind of upslope and this is downslope. And so the question that they were trying to get a handle on is there's kind of 2 different stream systems that could be happening. Is if we get saline water coming from the irrigation region charging into the stream, that's called a gaining stream, and it can cause salinization because you have the saline water coming in. Another mechanism is if you have fresh water from the stream that's actually leaving and propagating into the groundwater system. And so that's reducing basically how much water is in the stream. So that can be another mechanism for it becoming more saline. And so the interpretation here that was originally presented by Vizzoli is that there's kind of 2 different regions happening within that same stream. So these blue regions were below the stream by about 8 meters here. These blue regions that are resistive are regions where we're losing fresh water from the stream. And these regions that are perhaps more conductive are where we've got this saline groundwater actually coming into the stream. So this is an example that will be posted in the Simpeg documentation soon. And so if you're curious to run that yourself, we'll have that up and running. And if you want to run it today, feel free to send an email and we can get you the instructions. So I talked a lot about the EM implementation in Simpeg, but there are other methods that we have access to and we have implemented. So we've got potential fields. As Doug showed last week, we've got DC resistivity and IP. With electromagnetics, we have both frequency and time domain. We've got the EM1D, but we also have it implemented for 3D simulations. Oh, and this should say controlled sources and natural sources. We do have a natural source implementation within Simpeg. And we have fluid flow for Richard's equations. I also want to highlight some of the work that's ongoing in terms of efficiency, and Dom has really led some of the charge with getting sort of tiled inversions up and running. And so if we want to solve parallelize a 3D problem and solve sort of subdomains of a given problem and map that back to a larger mesh. That's in progress. And so that's something you can look forward to if you're interested in running larger 3D inversions. So I've talked a lot about the code, but I want to pose the question perhaps, what is Simpeg? And I want to suggest to you that it is a lot more than the code. This is really a collaborative project with folks from quite a number of different institutions. So when we originally started it, it was primarily at UBC, but we've got contributors from quite a number of different universities as well as companies at this point who are using and contributing and improving and fixing it. So the website, if you're curious to read and connect to the documentation, anything like that, is Simpeg.xyz. And so Simpeg is an open source project. It's openly licensed, MIT licensed. So anyone's welcome to download the code, take it, do what you want with it, adapt it. But we also welcome contributions back and have this sort of structured as a community-driven project. And so there's a few things that you need to have in place to have multiple people working in one code base at once. And so there's things like software practices. So we've got the code, it's up on GitHub. We release versions regularly, new versions. We have issue tracking there. You can suggest changes through what's called a pull request, and those are all peer reviewed before they are brought into the main code base, and often go through a bit of an iterative process of improvement, thinking about naming, adding tests and such. There's also practices for sort of communication and keeping folks connected and chatting through problems and working on the code base together. So we have weekly meetings. They're on Wednesdays, actually. It'll be after this. It's at 10:30 Pacific. They're all recorded. They're up on YouTube. So if you're not able to join but want to follow along, you're welcome to. We have a forum where you can come and ask questions. And we also have a Slack group where you can come and chat, and we often post, that's where we post the links for the weekly meetings and things like that. And so that's all accessible through the Simpeg website. One thing I want to focus on sort of specifically for a scientific community is the code testing. And so I wanted to just touch on this briefly, because when folks talk about software engineering and you talk about unit tests and things like that, we talk about sort of testing, modular pieces of code. And there's places where we can do that. So there's places where we've got, mathematical identities where we know vector identities should be satisfied. We know that the divergence of a curl should be 0. And that's something that we can check and we can assert that is true. But as we start to get to more complex scenarios, it can be challenging to test code. I mean, some places we've got analytical solutions. So in EM, we know we've got lots of solutions for spheres. And so that's a good place to test the code, is we can check that, slightly more complex behavior is correct. But if we get to a full on 3D EM simulation, we don't know what the answer is. And so we can do things like code comparisons. And so Dieter has led a paper that we've got submitted right now. It's in review, but it's posted on arXiv, and I've got the link in the references, where we've done a code comparison between 4 different code bases that are all open source in the Python ecosystem. So EMG3D being the code that Dieter has led. So staggered grid code as well. And then there's 2 finite element codes that we compared with. So custom and petgem are the 2 other codes that we compared with. And so we ran a few different examples, layered earth block model, but then actually looked at the marine CSEM Marlin example, which is quite a complex geometry. And so it's somewhat insightful to go in and sort of see where the details and things like that differ. And so the point I want to make here is kind of, a bit of the testing mindset. So first of all, having code tested is important in order to enable folks to be able to come in and suggest changes and things like that. You want to make sure if somebody suggests an improvement, that doesn't have sort of downstream negative implications. But if you have good testing on your code base, then you can develop and sort of include changes with a lot more confidence, because you do know you've got sort of these checks in place. But as we sort of think about how to design tests and how to write tests, it's really about building confidence that your code is working correctly. We can't assert that our 3D EM simulation, we don't have ground truth to really be able to completely validate or prove that it is working. But by running comparisons and things like that, you can build confidence that it is doing what you expect. And then I mentioned a few of the community resources and ways to connect. So we've got documentation. And I want to give Devin a shout out for this, is he's been working very hard on developing tutorials and examples that are useful for the community. And so if there's examples there that you find useful, Devin is probably somebody who deserves some credit there. We've got chat if you're interested in coming to connect with folks, both on the discourse and on Slack. And then all of our meeting notes and the recordings are available online. And so, the documentation is such an important piece for any sort of community-driven code or code that you want others to be using. And another piece that is quite important is really sort of the theory and the context around that. It's not enough to just have basically step-by-step instructions for running an inversion. being able to actually, promote sort of critical thinking and sort of critical analysis of an inversion result is quite important. And Doug talked on that last week. And so another thing that we've been trying to do is collect and develop educational resources and sort of reference resources on electromagnetics, on inversion. And so this is all under the GeoSci umbrella. And so the main website and landing page is GeoSci.xyz. There's a few different resources there. For those of you who attended the DISC or know about the DISC in 2017, the SEG, the Society for Exploration Geophysics, puts on a course each year and invites an instructor to go around and give a one-day course. And so we led the course on electromagnetics. So Doug was invited, and I was fortunate to be able to attend some of those and present it with him on that, as was Sagi. And so for that, we developed the electromagnetics resource, this EM module. And then one that is currently under construction, and we are excited to ask for contributions and ideas, is an inversion module. And so Doug showed this last week, and so it's currently under construction here on Curve Note. So please come take a look if you've got ideas on things you would like to see in there, questions you would like to see answered in there. Feel free to get in touch. As I mentioned, we'd be very happy to have contributions. And so, the idea of GeoSci is kind of to be this umbrella of supporting content that really does, it acts as a resource for folks who are interested in solving applied problems with geophysics. And so with that, I'll leave you with a few links, and also want to say thank you all to the Simpeg community. It's a large community, and I'm happy to be able to represent today, but none of this would have happened on my own. And so this group of people here is to thank for where Simpeg's at and the wonderful work that's being done there. I also want to thank Alan and Max for hosting me today as a part of the EMinars. Thrilled to be able to connect with this community and share what we're up to. And so if you have any questions today, or if you are curious to take a look at Simpeg or GeoSci and have suggestions, ideas, please get in touch. It is a community-driven project, and so we're excited to get contributions of any form.
Right. Thank you very much, Lindsay, for this nice presentation, and also sort of teaching us a bit about this tremendous resource. So we're going to move to the question and answer session now. So please start typing your questions. We already have a few in, but I'm actually going to, if you want to abuse my power as convener, for a comment and a question. So the comment, so if you want this, I want to mirror your sentiment on testing, because that's something I've been using a lot, and I find it extremely helpful to catch mistakes. And actually, my first contact with Simpac recently was that I used Simpac to test my own implementation of a magnetics code, because I had some trouble sort of understanding what was going wrong, and I decided, okay, there is somebody else who knows, who should be tested. And so that was a great help to find out, where am I going wrong, and how should things look like. And then maybe the question, so you were talking, for example, about the cooling scheme for the regularization. Now, of course, the applicability of that depends on your inversion method. So if you use something like an NLCG, then you can't do this because your current step depends on the past history. So do you have any, if you want, so mechanisms in place that the user can't do something like this, or is there sort of use at your own peril? Sort of how much user responsibility is there in this universe? So
there is, for example, if you didn't want to use the beta cooling schedule, all that would change in sort of what I showed is you just leave that directive off. You just don't include it in there. So it is something that that flexibility is there. And then I guess in terms of guardrails and things like that for checking, if things are compatible or not, if you shouldn't be using the beta regularization, or sorry, the beta cooling schedule. We did have some checks in some places, but a lot of this right now is it's up to the researcher to use the flexibility responsibly. And so if you design a crazy scheme or something that is kind of incompatible, I can't say that we guaranteed have checks in place to stop you from doing that.
Yeah, and I mean, that's exactly why I'm asking, because of course, these things are a tremendous amount of work to sort of combine all the eventualities and check for that.
Mm-hmm.
Okay, so let's move on to the questions from the audience. So the first one is from Marc Vallée. Do you have a publication on your work with a book? I can't pronounce the book pronoun. So the groundwater work.
So we did publish an inversion in the 2017 paper where we talked about Simpeg EM. That one used the cylindrical meshes. And so since then, Simpeg EM1D has been implemented. And that example that I showed today is in progress. We're working on getting it included in the documentation. So it should be included in the documentation in the relatively near future.
Okay, thank you. And then Mohamed Gomar, do you have a specific program or code to simulate the electrical properties of rock?
In terms of, I guess, perhaps asking about upscaling, is that kind of?
Well, I suppose something like Archie's law, or sort of, going from geological quantities of geological interest to electrical resistivity. That's how I understand this question.
Okay, yeah. So there's some pieces of that implemented. So if you did want to do something like Archie's law, that would be relatively straightforward. Soggy's been doing a lot of work kind of looking the other way of going from electrical conductivity or resistivity to lithologies in groundwater applications. And Doug also mentioned Thibault's work last week, and he's been looking at petrophysical inversions and petrophysical and geologic inversions. And so that is, again, also sort of an approach for getting physical properties from inversions, or sorry, geologic models from inversions. So that's going the opposite way, but going in sort of the forward sense of something like Archie's law. Those things, we haven't spent a lot of effort on kind of implementing that, but with simple relationships, that should be relatively straightforward.
Yes, I suppose in Python, yes, you can roll your own if you have at least a functional relationship.
Mm-hmm.
Okay, Syed Mohammed Foroshani, thanks for your interesting presentation. Which preconditioner do you use in the forward modeling? For instance, do you use Roddy and Mackey's preconditioner? And is the code able to use adaptive mesh too?
So for the forward modeling that I showed, we used a direct solver. So we used the Paradiso solver, so we didn't need a preconditioner. But if you wanted to use an iterative solver or plug in your own, that can be done. And then in terms of adaptive meshes, we do have the Octree implementation. So that is a bit of an adaptive mesh that you can use to focus where you refine the model and kind of spend computational effort.
And actually, there's a second question from Syed as well. So how do you add the boundary condition between the cells and the Earth's surface into your coefficient matrix if you do not use integral equations in your forward modeling? And how do you add sharp geometrical boundaries into the media? So for the Air-Earth interface, in this case, we do actually just assign physical properties on the mesh. So we assign physical properties of the air and of the subsurface. And so there's sort of nothing special that we need to do at the Air-Earth interface. Yes, I think sort of for finite difference, so you're using a finite difference approach, right?
A finite volume.
Well, finite volume, yeah, but yeah, there are the standard procedures for sort of dealing with the boundary conditions.
Yes, yeah.
Okay, Mohammed Hibatullah, Thank you, Lindsay Higgy and team who contribute for Simpac. I have a question about the joint inversion process. Is Simpac supported with joint inversion feature for different physical properties, i.e. density and resistivity? And how do we define the coupling parameters, for example, cross gradient or petrophysical relationships?
So in terms of joint inversion, the pieces are there. So if you did want to go ahead and run a joint inversion between gravity and magnetics, the pieces are there. So Thibaut has done some of this. Also, Jaja's group at the University of Houston, they've been looking at joint inversion. But right now it's still sort of at the early research stages. And so the cross gradient is not fully implemented yet. We're working on that. And so right now it would kind of be up to the user to define and piece together those pieces. And so it's not sort of a out of the box process yet.
Paul Wilkinson asks, thanks for an excellent talk, Lindsay. Is it possible to use an extended source, such as a large coil, rather than an idealized dipole in Simpac?
Yes, that's all possible.
Okay, and Oleg Borovko, excellent presentation. It's also great how Simpac packages modular code. The documentation is focused on Anaconda, which works very well in the Windows environment. Where can you find documentation on the configuration in Linux?
So Anaconda and Miniconda should also work on Linux. And so I would actually suggest starting by taking a look at sort of the Miniconda documentation, which is a bit more lightweight than Anaconda for Linux. There is a distribution there. Yeah,
and I mean, I'm using Linux and I've run Simpac on Linux even without Anaconda. It's a bit of sort of finding the right packages, the dependencies, but it can actually be installed relatively easily. So I don't think there's a principal difficulty there once you're familiar with how Python and the packages work. Another question from Sayed Foroshani. Which distance is enough to go away from the inhomogeneity to satisfy the boundary conditions at the borders of the media? For example, Wanamaker used a distance of about 8 skin depths away from the anomalous body.
Yeah, so looking at the skin depth in frequency domain or the diffusion distance in time domain is generally sort of the rule of thumb, and you want to go, typically multiple skin depths or diffusion distances, more than one. And that's something that you can test, is that, if you go out 2 skin depths and then you go out 4 skin depths and you go out 8 skin depths, if those solutions are all the same, then that you can perhaps do 2 to 4. If you see that that's changing, then you'll want to go out further.
Makoye Didas, thanks for the presentation. Does Simpac perform inversions of MT data?
Yes, we're actively working on improving the natural source EM implementation in Simpeg right now, but we do have the capabilities for MT simulation and inversion. But it is kind of that's a part of the code base that's a bit under construction, and so looking for folks who are interested in testing that out.
And Sayed Foroshani again, which line search method is used in Simpac?
We do have line searching implemented, a simple sort of backtracking line search. If you wanted to implement something fancier, that can all be plugged in.
Yeah, so do you rely there on some, I suppose, some Python optimization packages, or do you roll your own?
We roll our own for that. And so if you look at the if you look at the optimization module in Simpeg, there's a lot more details there and sort of the different techniques and approaches you can use.
Okay, and then Vikas Baranvai, excellent talk. What were strengths and weaknesses of the 2 methods when comparing NanoTem and Resolve for near-surface structures?
I mean, so they're both different systems, and you deploy both in different scenarios. So NanoTem is a ground-based system, whereas Resolve is airborne. So airborne, you can cover a lot more ground in the same amount of time, but on a ground survey, you could perhaps put out more receivers and things like that. And so in a sense, it really depends on like what question it is you're trying to ask. And so for us, this was just a bit of an example of, you know, comparing a few different systems in time and in frequency and seeing what we can get out in each.
Yeah, actually, I have related to that example. I have one question. So you were showing, okay, you have time domain and then, oh no, you had frequency domain and you had two different types of time domain with slightly different steps. Mm-hmm. Is there a capability, or is it even automatic, that if you have the same time steps in the two different, I forgot the names, NanoTem and SkyTem, that it sort of avoids redundant computations, or is that still tricky?
So that's something that would be up to the user to configure. If you knew that you were using one specific system and could get away with one simulation, that would be up to you. But for each source, if we have different waveforms, you're going to need to do computations for each. So yeah, we don't have anything that's sort of looking at what you've set up and then trying to be clever about it under the hood right now.
Yeah, and again, of course, that's something that is first of all tricky, and of course, second guessing the user can also be quite dangerous.
Yes, so those things are up to the user.
Well, that seems to be it from the question and answers session. So again, thank you very much. That was very interesting, and yeah, I think a great service to the community, having these things available. So thank you everybody for attending, and well, I hope to see or hear most of you next week again.
Well, thanks for having me.
Right. Okay. Thank you and goodbye.